Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and the topic of our today's discussion is the description of a steam power plant. You know that we have discussed about the basic of thermodynamics, and we have done this recapitulation, or we have done this exercise only to recap what we have learned from the basic thermodynamics and those laws which we have learned, that is first law, second law. In particular, combine these two laws, the mathematical form of these two laws will be required to analyze several processes which are there in a steam power plant. So, today we shall briefly discuss about the steam power plant, because we shall be discussing several thermodynamic cycles which are used to describe the processes of steam power plant. We shall discuss about several pertinent issues required to modify and also to have smooth operation of the power plant in greater detail in our subsequent classes, but today just for the understanding what are the different processes constitute to form a cycle which is used to describe the performance and operation of the power plant, and that I will discuss today. Alongside that whatever we have learned from our previous classes, that is first law applied to steady state steady flow process, and the second law, we shall see the applicability of these two laws in the context of the analysis of several processes which are there in a steam power plant. So, what I will do today, just I will try to describe several processes in a thermal power plant, but if you try to recall, in one of the previous classes I have listed down a few important points. One of the important points is if you would like to analyze the process or processes which are there in a system, our first objective should be to have the schematic depiction of the system. Only then we can easily go to the next steps, essentially to have an not I mean qualitative, rather both qualitative as well as quantitative estimation of the efficiency. So, if we try to discuss today that block diagram of steam power plant. So, you know that I am trying to just represent not all components, but the major components which are used to which are used in the power plant. The first component is boiler, and next important component is turbine, and I would like to discuss a few important issues before I go to discuss about the rest of the components of this particular system. So, what is done, that in this particular device, mechanical device or component, whatever you would like to say. So, in this device or component, the working substance, which is again another important points, if you try to recall, we have discussed. So, first we need to depict schematically the system, then we need to identify what is the working substance. So, in this steam power plant, working substance is water and other steam, rather steam water mixture. So, you know that if we allow water to go into the boiler, this is a mechanical device. The working substance, upon receiving heat from external source, this working substance, when it is entering into the boiler, upon receiving heat from an external source, converted into steam, and that steam is taken into another mechanical device or component, that is called turbine, of course steam turbine, wherein that steam is allowed to flow, and while steam is flowing through this turbine, it does work on the rotating part of this device. Okay. So, that it is not so straightforward, that I have drawn it schematically by just showing these two components, but in real application, real practice, you will find that the steam which is coming out from boiler is not directly taken into turbine, rather steam is allowed to pass through flow nozzles, of course to achieve some stated purpose, and then only when steam is coming out from the flow nozzle, it is directed to the turbine and it impinges the turbine blades, and by virtue of momentum change, the rotating part of this turbine, that is called runner, rotates, and that the turbine blades are mounted on this shaft. So, this is called turbine shaft. So, this is turbine shaft. So, these blades are mounted on this turbine, on this shaft. So, as blades are rotating, turbine shaft will rotate, and this shaft is common. So, this shaft is connected to the shaft of an alternator through mechanical coupling. So, you all have studied coupling in machine design course. So, basically this shaft is connected to the shaft of an alternator through mechanical coupling. Since the turbine shaft is rotating, so the shaft of an alternator will rotate, and from there we will be getting electricity. If we do not discuss that part, because that is beyond the scope of the discussion in this course, so what we can understand, at least you can see. So, upon receiving some amount of energy in the form of heat, that energy is getting converted into work. So, basically that if it is a system, in this system we are supplying energy in terms of heat or by heat, and we are getting work output from the turbine. So, that is energy out from the system in the form of work. So, what I would like to tell you, that I did not complete the circuit. So, I did not complete the circuit, but I would like to discuss an important issue. So, now question is, today we shall try to discuss about the applicability of first and second laws in the context of the operation, in the context of the description of several processes which are there in a steam power plant. So, you can see that if it is a system like this, we are supplying water, we are supplying heat maybe by burning coal if it is the thermal power plant. If it is diesel fired boiler, so maybe diesel will be used to burn, and out of this combustion process energy will be utilized to heat up the water which is circulated through the boiler, and when it is being circulated through the boiler, it will be converted into steam, and that steam is taken to turbine through flow nozzles. I did not show the flow nozzles, perhaps not perhaps, rather I will be discussing this flow nozzle again in one of the subsequent lectures. So, that we are getting work output, but question is here the second law is coming into the picture. So, first law is which is nothing but the statement of energy conservation is valid, right. What we can see that we are supplying energy in the form of heat, we are getting or we are extracting energy in the form of work. So, what second law tells us, I will be coming to that particular point, but let us again look at it. See, this is not a case that we need work output, to be precise, electricity from this particular system only for a single time, rather we need to have it in a cyclic, rather in constantly. So, we need constant work output from the system, which in turn will ensure that the electricity that will be produced from the alternator will be will supply constantly. Okay. So, if we need to have constant work output, that you have to have continuous supply of water. It is very unlikely to believe that while steam is expanding in the turbine, that steam will come out, right. So, after doing some amount of work, when steam is coming out from the turbine, it is having less energy, right, because steam is doing work while flowing through the turbine, and it does work. So, basically that but after doing work, that steam will come out from the turbine. So, if I show over here that this is the steam which is coming out, that you have studied in thermodynamics that though we are trying to discuss that heat and work, this two are the two different forms of energy, right, but that there is a distinction between these two energies, that is one is low grade energy, other is the high grade energy. So, try to understand the amount of heat which is added to the boiler, right. The amount of energy which is added to the boiler in the form of heat is not equal to the amount of energy we are getting or we are extracting from the turbine in the form of work. So, all the energies, all the thermal energy to be precise, that is entering into the turbine is not getting into converted equally to another form of energy, that is in the form of work, while certain amount of energy is coming out. So, it in a way is trying to say something that we have learned from second law. If you try to recall the Kelvin-Planck statement, what is Kelvin-Planck statement? The statement is, it is impossible to construct a device which will operate in a cycle, and the sole effect will be raising weight or producing work while exchanging heat with a single thermal reservoir. So, this is the single thermal reservoir, because this is a device where heat interaction is there. this is a device in which we can see only work interaction is there, because though I will be discussing, but for the time being I can tell you that turbine surface is insulated only to ensure that while steam is expanding there will not be loss of energy. So, the thermal energy at the inlet to the turbine will not be, there will not be any loss of thermal energy from the flowing steam because of this transfer of heat from turbine to the ambience. So, that is why turbine surface is insulated. So, even then you can see this is only the work interacting device, because no heat interaction between system and surroundings. This is on the other hand a device in which heat interaction takes place. So, you know that in this device there is no work interaction between system and surroundings, only heat is supplied to the system from the surroundings from an external source. Only what I would like to tell you, that following second law of thermodynamics, if we need to have constant work output, so that means this will be a cyclic process. If we need to run it in a cyclic manner, it is not possible to construct only with a single temperature thermal reservoir. So, we must have another thermal reservoir in which heat must be rejected to the surroundings. So, that is what I would like to tell you. So, try to understand what I am telling, that if it is a once through case, we are supplying water, we are getting work output for a particular duration, and then after doing some work, steam is ejected to the surroundings. If it is a case, then this is fine, but if you would like to ensure that the work output will be continuous, and then only second law is putting a restriction that this is not possible at all while exchanging heat with a single thermal reservoir. So, there must be another device or reservoir in which heat must be rejected. So, this is known as condenser in which heat is rejected. So, if I give this is Q in, that is heat is added to the system, that is heat is getting into the system, and this heat is Q out, that heat is coming out or from the system or is getting rejected. And you know that this is not possible, because after rejecting heat, the steam which is coming out from the turbine is still having some thermal energy in the form of heat, and that heat energy is getting rejected while it is coming in this device, that is called condenser, and the collected condensate can be pumped back to the boiler to make it a cyclic device. So, we may have we should have one pump. So this is the basic description of the steam power plant. We shall be using, rather we shall be drawing this basic schematic frequently when we will be discussing several issues related to this particular system, thermal power plant system. So, this is a cyclic system. So, all the processes are executed in a cyclic manner. So, basically you know that till now it is not completed. If we have such a system, we can ensure that the work output from the turbine will be continuous. Second law permits that. So, there is a thermal reservoir in which heat is added, there is another thermal reservoir in which heat is rejected. So, this is permitting us to construct this device which will operate in a cycle. If we can ensure that this will operate in a cycle, we also can ensure that the work output from the turbine will be continuous. If it is so, then there will not be intermittent supply of electricity. So, basically electricity that we are expecting to get from this plant will be continuous. So, now you see that heat is added to the system, work is coming out from the system, heat is rejected from the system, but also to run this particular device that is called pump, we also need to supply some amount of we need to supply energy. So, we need to supply energy in the form of work. So, this is called W in. So, this amount of work addition is required to operate pump, that will be used to supply condensate from condenser to the boiler pressure, that I will come to later, but for the time being you please do not consider boiler, what is boiler pressure. So, this pump will be required to supply condensate from condenser to the boiler, and for that we must require some amount of work that would be added to this device. So, this is W in and this is W out. So, effective work output should be that W out minus W in. So, this is the W out we are getting, but try to understand a fraction of that work output will be required to operate the pump. So, eventually the net work output will be, so if I try to write, the net work output will be W out minus W in, right. So, what is the conclusion? Now, I will be coming to the first and second law and to see their applicability to describe the processes, but you understand that to operate this system in a cyclic manner, essentially to ensure that the work output from the turbine will be continuous, there must be a thermal reservoir in which some amount of heat must be rejected. See, this is again something contradicting. Why? We are supplying energy in the form of heat to the boiler, as I have said that this energy supply will be through burning of coal or by burning diesel. Whatever is the case, we are supplying energy and a part of that energy is used to convert work to another form of energy, while remaining part of energy is rejected to the surrounding. So, it is somehow contradicting the feasibility of operating a power plant essentially from the economical point of view. So, you know that by burning coal we are supplying energy, and out of that energy part of the energy is again rejected to the surrounding, right. You know that by how this energy is getting rejected to the surrounding we will discuss, but what I need to discuss at this point is that it is something contradictory. So, this burning coal, for that again some mechanical arrangement is required, the energy which is supplied to the boiler, for that again mechanical arrangement is required. So, by so many mechanical arrangements the energy is supplied, but after supplying energy we can see that some amount of energy is getting rejected. Our objective should be to reduce this amount, but at least we can see from second law that second law puts a restriction that there must be a heat sink. So, otherwise we cannot run this in a cyclic manner. From there I am telling, so this is an essential component for this system to run this system in a cyclic manner, but in this system rather this system is acting just like a this device is acting just like a heat sink. So, our objective should be to minimize this quantity, essentially to maximize the efficiency of this plant. So, upon minimizing this quantity we can maximize the system performance. So, attempts should be taken to minimize this quantity. So, there are several issues, several modifications we will discuss, but now second law is putting a restriction on this, that this will be there. So, if we need to go for minimization of this quantity, keeping in mind that the efficiency or performance of the plant will be maximum, we need to invoke the first law, which is used to the flow processes. Why? So, now try to understand that the water is continuously flowing through the tube which are there inside the boiler, and heat is supplied or heat flow is there over the tube. So, by virtue of heat exchange, water will be converted into steam. Again steam is coming from the flow nozzle and it is entering into the turbine, again it is a flow process. So, if we know that amount of heat which is added in the boiler, the amount of work which is coming out from the turbine. So, if you would like to calculate the amount of work which we are getting out of this energy conversion, that we know, that we must know, but we only can calculate by applying first law of thermodynamics to a process which is steady state steady flow. So, now requirement, so you have understood that the second law is very much needed to understand that we cannot run this device without cyclic manner if we do not reject heat to the surroundings. Next is, having established the fact that we must reject some amount of heat to the surroundings, next question is, can't we try to reduce or minimize it? Why? Because our objective to maximize the system performance. If we are planning to do so, at least we must know what are the different processes inside all these 4 different components, and then only what is the amount of work output, what is the amount of heat is added to the system can be estimated. So, by doing that we can minimize this quantity, but if you would like to know the amount of work that we are getting out of the out of this particular process which is there in the turbine, the amount of energy which must be supplied to the boiler to convert steam, all these processes are important to know, and for that, so basically energy conversion. So, the amount of energy added here, amount of energy you are getting here, amount of energy rejected here, and amount of energy is added this device. So, all these 4 devices energy either is added or energy is extracted. So, to know that we need to apply first law of thermodynamics, but applied to the steady state steady flow processes across the control volume. So, here it is that you cannot treat the control mass system, because mass is, even though you can consider that at any particular instant when you are trying to calculate this or you are trying to have this energy balance, mass is remaining constant, but this is not a control mass system. So, this is basically control volume system. So, net we are trying to write. Similarly, we can write here is that net heat input, that is Q net, equal to Q in minus Q out. Okay. Next, we will be discussing about the first law of thermodynamics applied to steady state steady flow processes. So, let us write it, steady state steady flow processes SSSF. So, now let me write here what I am not going to just I will write, we have derived this expression. So, if we write, so this is a process across the control volume. The first law of thermodynamics which is applied to a steady state steady flow process, okay, and this is applied across the control volume. Okay. So, if we write, we are getting Q dot minus W dot equal to, we can write that m dot E H E plus C square by 2 plus G J D minus m dot I H I C I square by 2 plus G Z I. We have not considered dCV dt because this is steady state steady flow process, right. The state is steady and also flow is steady. So, the totally, that is the product of energy and mass within the system is not getting changed or is not changing with time. So, product of mass as well as energy, specific energy of course, within the control volume is not changing with time. So, that is the meaning of this, and that is why we did not consider dCV dt. Okay. That is change of energy within the control volume. So, this equation we have ignored, you know, that d dt Cv equal to 0. So, energy, this is exact differential. So, that is we have not considered. If the state is uniform state, this d dt Cv within the control volume, say I am writing for the sake of completeness, say we have one control volume and we are having energy in, we are having energy out, and the control volume is undergoing through a process, and so basically say the system is changing from states 1 to 2. The control volume, this is the control volume. So, this is exit, this is inlet. If the control volume is undergoing through a process and by virtue of which it is changing its state from state 1 to state 2, and if the process is following or process is occurring following uniform state, uniform flow, right. So, uniform state, that means maybe the control volume is changing state from state 1 to state 2, but at any instant of time energy state is uniform throughout the control volume. So, that is what is important. The control volume is changing its state from state 1 to state 2, but at any state, say state 1 or state 2, at any temporal instant the energy state is uniform throughout the control volume. If it is the case, so basically for uniform state, right, we can write it that q dot minus w dot equal to, if we have single exit and single entry together with the mass balance. So, we can write me He plus C square by 2 plus G J D minus Mi Hi plus Ci square by 2 plus G Z I. Since it is uniform state, we cannot make this term trivially 0. So, basically this should be plus E2 minus E1 plus E2 minus E1. That is E2 minus E1. So, you know that this change in energy, that is within the control volume. So, this is basically that energy into the system or control volume by heat, energy out from the control volume by work. This is energy out from the control volume due to flow, energy into the control volume due to flow, and this is the change in control volume. So, this change in energy within the control volume. So, this E2 or E I am writing, that is U plus C square by 2 plus G Z So, is u plus c square by 2 plus Gz, but it is not H, because it is the thermal energy for the non-flow system. So, this is basically, if I use suffix 2, then it would be u2, c2 and Gz2. If it is suffix 1, it would be u1, c1 and Gz1. So, basically this is the change in energy within the control volume, and this change in energy has nothing to do with change in energy due to flow. So, here try to understand, this is basically, again I am telling this q dot. So, that is energy input to the control volume by heat, w dot, this is energy output from the control volume by work. First quantity, that is Me, multiplied with this quantity is the energy out from the control volume by flow. So, because flow is continuously there. So, this is flow in and this is flow out. So, this is flow out and this is flow in, and so this is the flow energy. So, flow out, energy out from the control volume due to flow, and this is energy into the control volume due to flow. This term will be there if the process is occurring following uniform state. So, that means this is change in energy within the control volume, and that quantity we have written. For most of the processes which we shall consider to describe for this system, we shall assume that the process is or processes are steady state steady flow processes. In that case, you can make it this quantity, so there is no change in energy within the control volume, and as I told you that steady state, that is energy state, is steady. Energy state does not change with time, but energy conservation is not done in an isolated manner. As I told you, it has to be coupled with the mass balance. So, basically you know that this is the equation for the steady state steady flow process. So, if we try to differentiate this process from this uniform state, this term is there for this particular case, because this is the change in energy within the control volume. So, let me write. So, this is change in energy in the CV. Okay. So, that term is 0 for this case anyway. So, this is the first law of thermodynamics applied to steady state steady flow processes, and as I told you that we shall be assuming that all processes are steady state steady flow processes. Okay. So, this is rate equation. If we integrate it over time, then so this is rate equation. So, if we integrate this equation over time, then we will be getting cube minus W equal to M E H E plus C square by 2 plus G J D minus M I H I plus C I square 2 plus G Z I. So, you know that here also we have assumed that we have taken only single entry single exit. Let me tell you, this equation is valid only under an important assumption, that is H, velocity and G. So, these three properties do not vary across each flow section. So, this equation is valid under an important assumption is that properties like H, C and Z, these properties do not vary across each flow section, only then we can. So, if you can recall that when we have derived this expression, we have taken out this out of this integration, out of the integral. So, basically, so this is what is important. Okay. So, we are writing this. If we try to write in a specific form, so basically you know that we can write del cube in differential form, del cube minus delta W equal to M E H E plus C square by 2 plus G J D minus M I H I C I square by 2 plus J Z I. We also can try to write in specific form, that is small delta cube plus H I C I square by 2 plus G Z I equal, rather we are trying to write in specific form, H E plus C square by 2 plus Z E plus delta W. So, this is which is very important, and we shall be applying this particular equation while describing several processes in this particular system. So, now I shall try to discuss about why we need to know the energy which is added to the system. We also need to know what is the amount of work we are getting from the system. We also need to know what is the work added to this device. So, if we can calculate, so basically if we know that what is W out and W in, we know what is Q in, from there we can easily calculate what is Q out. This particular quantity is very crucial, because our objective should be to minimize that particular quantity to ensure that the efficiency of the system will be maximum, right. So, now let us first focus on this particular device, that is boiler. So, again if we assume that the process which is there inside the boiler follows the steady state steady flow process. So, if we write the boiler, so let me write here, I forgot to write here, you know that B stands for boiler, T stands for turbine, definitely it is steam turbine, C stands for condenser, and P stands for pump. Okay. So, these are basically I have used short form to identify. So, basically now let us go to this particular case, boiler. So, if we try to write this equation, we write del cube plus H I plus C I square by 2 plus G Z I equal to H E plus C square by 2 plus G Z D plus delta W. What I told you now, you know that this is the equation we shall be applying. So, that steady state steady flow equation applied to the process which is there inside the boiler. So, steady state steady flow process in the boiler, we can write it as I told you, you know that the work done required to maintain the flow in the presence of pressures. So, basically you know when we have written this equation, in this equation we have considered the work done required to maintain the flow in the presence of pressure, and that work is coming in this term, but here control volume is not doing any work. So, this delta W takes care of any work that is done by the control volume. So, either work is done on the control volume or work is done by the control volume. So, that is taken care by this term, while you may argue that while water is flowing through the steam, definitely we need to do work, because we need to maintain the flow in the presence of pressure, but that work has already been considered in this term H E, but since there is no work done by the control volume, so this term is equal to 0. So, that is why boiler is not a work interacting device, control volume does not do any work. So, and also if we consider that the changes in kinetic energy and potential energy are negligible. Then, so basically Ci square minus 2 minus C square by 2 and G into Zi minus Jd. So, if we consider that C square minus Ci square by 2 almost equal to 0 and Jd minus Zi, this is almost equal to 0. So, that is changes in kinetic and potential energy. Okay. So, if this is the case, then we can straight away write this delta cube equal to He minus Hi, right. So, the amount of energy that should be added to the boiler, right, or we can write that cube 1 to 2 equal to H2 minus H1. Either we can write in this form. You must know that this heat and work, these two are not the exact differential. So, the amount of heat addition, the amount of heat that must be added to the boiler will be change in enthalpy of working substance, between inlet and outlet. So, if we can calculate the enthalpy of steam, enthalpy of water at the inlet to the boiler and enthalpy of the working substance at the exit of the boiler, the change in enthalpy is nothing but the amount of work that must be added to the boiler, provided the changes in kinetic and potential energy are negligible. So, this is what for the boiler. So, you know that similar way we also can apply the processes, steady state, steady flow processes in the turbine. So, let us briefly discuss about that. So, steady state, steady flow process in the turbine. So, we are assuming that the process that is there inside the turbine follows the steady state, steady flow process. So, we really do not know whether turbine is a work interacting device or the heated interacting device. Let us first write the generic equation, that is del cube plus Hi Ci square by 2 plus Gzi equal to He plus C square by 2 plus Gjd plus delta W, right. So, you know that again I am telling this is the heat addition in the form of, this is the energy addition to the control volume in the form of heat, this is the energy addition to the control volume due to flow, this is the energy out from the control volume by the flow, and this is the energy out from the control volume by work. So, now if we go back to the previous slide wherein we have discussed about the schematic depiction, you know that in a boiler just we have added heat from this external source, from an external source. In a turbine there is no heat interaction, and only to prevent heat loss from the turbine walls are insulated, while we are getting work output. So, this is the work which is done by the control volume. We also need to do some amount of work to maintain the flow while steam is entering to the turbine and while steam is coming out from the turbine. So, work done needed to maintain the flow at the inlet as well as at the outlet of the turbine in the presence of pressure, some amount that is already taken care of by this term HE and HI, but this additional amount of work, that is the work output from the turbine. So, on the top of this flow work, this is the amount of work done by the control volume, and that is what is important. It is because of this work we are getting work in only net work output. So, it is because of this work we are getting net work output, but the work done to maintain the flow either at the inlet to the turbine or at the outlet of the turbine has already been taken care by this term HE and HI. So, basically since turbine there is no heat interaction, so this term equal to 0. So, no heat interaction between system and surroundings. So, basically you know that if you also can consider these changes in kinetic energy and potential energy are negligible, then we can write. So, basically we are assuming, see now in the last slide also we have used E and I, but mind it, this E stands for exit from the boiler, this I stands for inlet to the boiler. Similarly, this E stands for exit, but since we are applying this equation to the turbine, so this E stands for exit of the turbine and this I is the inlet to the turbine. So, basically what we can do, taking this particular assumption, and since there is no heat interaction between system and surroundings, no heat interaction. So, when we are applying this process, when we are applying this equation to the process inside the turbine, so I can write that this delta W equal to that HI minus HE. So, try to understand, this is very important, or we can write W1 to 2 that equal to H1 minus H2. So, H1 is the enthalpy of steam entering into the turbine, H2 or HE, these two quantities indicate the enthalpy of steam leaving the turbine. So, the work done by the turbine will depend on the enthalpy drop inside the turbine, H1 minus H2. So, that equation we are getting from the first law of thermodynamics applied to steady state steady flow processes across the control volume. Okay. So, that basically we could see that amount of heat addition will depend on the enthalpy of steam at the exit of the boiler minus enthalpy of steam at the inlet to the boiler, while work output from the turbine will depend on the enthalpy of steam at the inlet to the boiler minus enthalpy of steam at the exit of the enthalpy of steam at the inlet to the turbine minus enthalpy of steam at the exit of the turbine. So, our objective should be, if we try to maximize this quantity, that is what I was discussing. Our objective should be to maximize this quantity. So, can we do something so that the enthalpy at the exit of the turbine should be minimum? If it is minimum, so we will be having maximum work output. That these are the several issues that we will come to know only if we can frame the equation mathematically. So, that we have discussed about the steady state steady flow process in the turbine as well as in the boiler. If we go back to this previous slide, we also need to apply the steady state steady flow process across the condenser. You can see, because I am not going to do this, the equation that the same equation, but we need to apply across the control volume. You can understand this again, this is a device in which there is no work interaction, only heat is subtracted or heat is rejected from this particular device. So, this is your home task, you can try. Again you can understand, if we assume that the changes in kinetic and potential energies are negligible, this is not a work interacting device. So, the heat rejected from the condenser should be the drop in enthalpy, that you can try. Most critical part is this fellow, because the addition of work needed to operate this device is very important. So, the work which is needed to run this pump, will it depend if the process is something adiabatic or process is isothermal? You can understand the temperature of the condensed water which is coming from the condenser is not very high, and that will be pumped back to the boiler. So, while it is pumping, whether the process is a reversible adiabatic process or reversible isothermal process, we need to identify. By identifying the process, then we will try to estimate the work done needed, and it would be quite interesting to see that the work done needed, whether it is a reversible adiabatic process or reversible isothermal process, is immaterial. So, the work done for both this reversible adiabatic and reversible isothermal processes will be same, and that we will do in the next class. So, if you would like to summarize, today we have discussed about this several components, at least major components which are there in the power plant. We have also discussed about the applicability of second law to describe the processes. Then by applying the first law of thermodynamics applied to steady state steady flow process across the control volume, we could establish the amount of heat that should be added to the boiler and the amount of work that we are getting from the turbine. Amount of heat rejected, the amount of heat which is being rejected from this condenser also a very important part, but that you can easily calculate by applying the steady state steady flow equation and suitably invoking the assumptions that we are that we have already considered. But the work which is added to the pump is also an important issue, because the net work output also will depend on the net work output from this plant, from the system, will depend on the quantity of this W in. So, in the next class we shall try to see the process which is there in the pump, and also by identifying the process what is the quantity of this W in. So, with this I stop here today, and we shall discuss we shall continue our discussion in the next class. Thank you.